Models, as we've talked about before, are so important for providing conceptual understanding to using decimals. And again, really any types of numbers. And often, too often, we rush into doing our calculations and doing our computations when we're teaching it, also before we've devoted the proper time to examining them using concrete models. People tend to feel better about using decimals than they do fractions. I've been teaching for 20 years, and students prefer decimals over fractions. They're more comfortable with them. One of the reasons that may be is because not only did we maybe not develop the proper understanding of fractions, but we missed out on the opportunity to show how fractions and decimals are linked and connected. And so we have to devote the proper time to examining decimals using concrete models, which is why you have your manipulatives that look something like this, what you see on the screen. We're going to do a couple different models. Primarily, we're going to be using decimal squares. That's going to be our primary focus. We're also going to look at number lines because that's also an important way to visualize numbers. But for the most part, we're going to be using these decimal squares. So you can see that we have tenths squares, hundredths squares, and thousandths squares. And the thousandth squares are a little more challenging to I think to see just because the pieces are so small. But I think they make the point of you're dividing this square into a whole bunch of tiny little pieces. Um, the tenths, right? There are 10 sections, and 3/10 is shown with three of those 10 sections shaded. We kind of use those same things when we were representing fractions of 3/10, right? They look the same. They're called the same thing. They have the exact same name. Sometimes we just want to use a number in a different form. This might look familiar, kind of familiar to the opening problem to the previous video, right? Where we had 100th squared and we had some of them shaded. So this is representative of 35 hundredths. Why? If we just start by looking at that three, well, it kind of looks like this, right? Here's an entire tenth. Here's another entire tenth. Here's another entire tenth. So just those are bad lines. Sorry. These represent 3/10 or 3/10. This is now five individual little squares out of 100, right? So that right there is 5/100ths or 5/100ths like that. And when we add those together, we get 0.35, 35 hundredths. There are 35 of those individual little shaded squares out of 100. You can see how decimals and fractions are completely linked. This is representative of the same thing. We could overlay the tenths on top of the thousandths, the hundredths on top of the thousandths, and we could do that same thing. Break it up into three vertical strips, and then see we've got 7/10, 500ths, right? So we could do that same thing here, right? Those five, or I said hundredths, but those 5 thousandths, right? We would see those right here, right? One, two, three, four, five, there. And so that's the idea of what these decimal squares are used for modeling decimals. Let's actually take a minute and look at this one in depth a little bit more. This 0.375, 375 thousandths. Let's examine this in its expanded form for a moment before we go any further. Right, what you can see is, again, the original decimal 0.375 can be written as 375 thousandths because of that last place value. If we separate it and look it into it in standard expanded form, we have this. And notice how they're all shown there written in thousandths, right? We're just separating it out. 375 thousandths is 300 thousandths plus 70 thousandths plus 5 thousandths. That should make sense to you, thinking back to our fraction chapter where we looked at common denominators. But another thing you can do is take each of these individual fractions here and reduce them still to a power of 10. 300 thousandths is the same as 3/10. That's what I was talking about here. There's our 3/10. There's our 3/10, okay? And then we have 7/100ths, right? These zeros can cancel out. It's like dividing both by the greatest common factor of 10, 7/100ths. And we would see, 7/100ths. We would see those like 7 stacks of these, right? About up to right there, okay? And then we have the 5 thousandths at the end. 3/10, 3/10, 7/100ths, 7/100ths, 5 thousandths. So it's so important to be able to link these things together. Understand where these numbers come from. They come from here. Those can be rewritten as this. That can be then added back together, right? So take a moment and just explore that, play around with that for a little bit, so you have a good understanding about that as well. I do want to show you another GeoGebra link that I have again in your Blackboard unit. This again kind of helps you see this a little bit better as well. So what we have here, this is as far as it goes, but it has a units place, then a decimal, and then it has the tenths place and hundredths place. And if you just click on the plus, you can fill in numbers in that hundredths place. Again, there's your decimal square. You can also add to the tenths, and it fills in an entire line. I'm going to take that away, and watch what happens though. 5, 6, 7, 8, 9. So predict what's going to happen when I click that one more time. What's going to happen to my number? I add 1, and this disappears, and now we have an entire full tenth right there. And I can keep going. I can do it again. 1, 2, 3, 4, 5, 6, 7, 8, 9. Predict what's going to happen. I click one more. It doesn't show it filled in the hundredths place because it completed a tenths bar, which appears here. It's carrying the 1, right? That's what happens when you add and you carry the 1. You can add this up to the ninths as well. You can probably predict what's going to happen if I fill this in. I filled in an entire single square, which now gets counted as 1 over here. I'll add this up to 9, and then I'm going to go to my hundredth cell. 1, 2, 3, 4, 5, 6, 7, 8, 9. Look what we have, 1.99. What's another way to read that? How would you say that properly? 1 and 99 hundredths. What happens if I add? Oh, it doesn't even let me. It doesn't even let me do it. I wonder if I could take away. Yeah, it doesn't allow me to do that. That's interesting. I'm going to take away this, see what happens if I fill this in. Yeah, okay. It was interesting that the programming on that didn't let me fill in 2. But if I use 0 and 99 hundredths, what'll happen if I click this? It adds another hundredth, which gives me 100 hundredths, which is just 1. Boom. So go ahead and play around with that as well. I think that's a nice tool for helping you visualize what's happening with your different decimal place values. So what I'd like to do now is have you do a problem kind of like I did earlier, where we look at a fraction. Let me give you a fraction. Linking decimals and fractions is very important. And I'm going to do one for you, and then I'll have you do one that's a little more complex. We're going to take this fraction, and we're going to describe, I want you to think about and describe, and maybe even model with your manipulatives, what the decimal square would look like that would represent this fraction and then write the decimal number. And so um, if I go back to here and just clear all these things out, this is what the decimal square would look like, 6/100. But then if we think about the expanded form, I want you to think about the expanded form of this. What we would have is 0/10 plus 6/100. When you're writing something in expanded form, you really want to give a value to every single place value. So this is our tenths place, this is our hundredths place. And if we think about how that would look as a decimal, then there would be 0 in the tenths place and a 6 in the hundredths place. So this would be written as 0.06, 0.06, 6/100, 6/100. So on your own, then try this one. This one's a little more involved. It's a little bit bigger of a number. And so do the same thing where you kind of expand it. Think about what the decimal square might look like, even though this is really big. 4728 over 10,000. See if you can write that in expanded form and then convert it to its decimal form. So if we go sort of place value by place value, we have to start with the tenths place. And so we might start this by saying this 4 is worth 4,000 10,000ths. That 4 is 4,000 10,000ths, which, if you cancel things, has a value of 4/10. Notice how the zeros can all cancel out. Plus, then we go to the 7. That has a value of 700 10,000ths, which, if you do some canceling, is 7/100. Notice it's in the, well, we'll get to that in a minute. Then go to the 2. 2, because of its place, is worth 20 over 10,000ths, or 10,000. Cancel that. Now we have 2,000ths. And our last digit was that 8. So we have 8/10,000ths, which we'll just leave as 8/10,000ths. What we're doing here is we're trying to figure out what number is going to go in each place value. And we can see from this that 4 is in the tenths place, 7 is in the hundredths place, 2 is in the thousandths place, and 8 is in that 10,000ths place. And what we have is 4,728 10,000ths, which is that place value. So we're sort of linking all these things together. We're linking the fractions with the decimals with those place values. Another way we can model decimals is using a number line. And in my experience, students often have a hard time with this. And so the first thing I'll do is illustrate what it looks like when you compare the decimal square to the number line. And what you'll see here is our familiar 0.3, or our 3/10 decimal square, where it's from 0 to 1 from the edge of the square to the other edge. And each one of the bars on the square is a tenth. And each one of the decimal markings is also in line with one of the tenths. So you can see that this here is equal to 1/10, which as a decimal is 0.1. This is in line with 0.2, etc. 3/10, 4/10, 5/10, etc. And when you fill in the entire square, all 10/10, now you are at 1. And so that can be a great way to link the relationship between what we call a region model, right? A region model, it's showing an area, and a linear model, which is just showing distance, right? That's the big difference. Area and distance. Some people do better with the area model at first because they can actually see space being filled in rather than just marking off sections on a line. But it is important to also be able to use the number line model. And so before we do our next little activity, I'll also show you a GeoGebra link here that again is in your Blackboard shell that that helps you if you want to play around with this, just make some sense and being able to visualize where numbers belong on a number line. And so what they do is they give you two decimal numbers, 8.5, 8.7, and you can see the markings there. And really it's what is the value of A? And so your job is to just look at that and say, can I determine what the decimal value of A is? And once you think you know it, the way you can use this little tool is to click, hold, and drag. And notice when we go from, we have 8.5 and 8.7, which means this line between them should be 8.6. So the distance from here to here is a tenth from 0.5 to 0.6, and then another tenth to go up here. So then your question was, well, what is each of these individual segments between them? Those are going to be the hundredths. So if you click and drag, this is 8.51, 0.52, 0.53, 54, 55, 0.56, 57, 58, 59, 56, or 8.6, 8.61, 8.62. You can also pull them back the other way, right? And so I think this is a really fun little tool to show you how, just how to visualize these decimals. Again, 9.9 and 10.1. If you pull from the bigger one back, notice how it's going to go down by 100th. 10.1, take away 100th, now you're at 10.09, 08, 07. And we get A at 10.03. You could also do the same thing, pulling it up. So that's just another fun little tool to pull around or play around with, just to help you make sense of decimals and place values and how they connect with the number line. So what I want to do now is look at a decimal number, and we're going to examine a number line. So the number is 0.372. And the first thing we're going to do is write this in an expanded form using those different base 10 denominators. So if I just go right to it, it would look like this. The 3 is in the tenths place, so it's 3/10. The 7 is in the hundredths place, so it's 7/100. The 2 is in the thousandths place, so it's 2/1000. So that helps us start this problem off. And now what we're going to do is zoom in on a number line. And so what we see here is this, imagine a long number line, right? Imagine you've got a number line, and you know, in fact, I'll just write a number line here, 0 and 1. That's not a 1, that's a 1. And if we cut it in half, now we're at 0.5. And if we cut this into 5 equal segments, 1, 2, 3, 4, 5, 0.1, 0.2, 0.3, 0.4. So those are our tenths places. We are at 0.372. So we can see right here, it's going to be 3/10 plus a little bit more. So this number, 0.372, 372 thousandths, is going to fall into this range right there. It's going to be bigger than 3/10, but not as big as 4/10. And that's what we see here in this zoomed in section, right? That little zoomed in section in that circle is really right in there, all right? And so the first thing we do is find out, well, where would 3/10 be, right? Where does that fall? So, right, 3/10 is right here. So our number, again, is going to fall in that zone. So the next thing we can do is examine the 7/100ths. So just like I showed you on that GeoGebra sliding scale, once we get into between 0.3 and 0.4, each one of these little indicators, 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10, those are going to be the hundredths places. So those we would be marking as 0.31, 0.32, etc. Right? And so each one of those is going to be the hundredths place. If that is a little confusing to you, I'm just going to do a little erasing here. Go back to our nice clean picture. One thing that can help folks is putting a 0 in the hundredths place and thinking about this as 30 hundredths and 40 hundredths. And then you can actually see the 10 spaces between 30 and 40, which would be 31 hundredths, 32, 33, 34, 35, 36, 37, right? So you can then maybe picture it a little bit better. So I'm going to paste the next little, it's not what I want to do. I need to give myself some more space here. Sorry. Let's delete you and move this down. That's for later. And here is a sort of a more zoomed in version about what we just talked about. So 0.37 would be that seventh mark, 0.38 is that next mark. So now we're looking in this little highlighted section here, right? We know our number is a little bit bigger than 0.37. We have 3/10, 7 hundredths, and now we're going to take this section and cut it up even further, right? We're going to zoom in. Right, so it's going to look not that one. Let me try one more time. Okay, so now we're going to take this little segment and expand it. Here's the 0.37. Here's the 0.38. And we're going to cut up this area into its own 10 segments. We're zooming in. Every time we zoom in and break it into 10 more pieces, we're going to the next place value. Like before, the 0.37, 37 hundredths, if you add a 0 to the end of that and do the same thing with the 0.38, now you're looking at it in the perspective of, or in terms of thousandths, 370 thousandths, 380 thousandths. So then you can count up 371, 372, 373. These are all thousands. And what was our number? It was 0.372, 372 thousandths. So it exists right here between 37 hundredths and 38 hundredths. Okay. And so you kind of have to, again, zoom in every time you're going to go into the next place value, right? So just rewinding a little bit to what we did, right? We started with our expanded view. We knew that we had to be bigger than 3/10. And then once we had those tenths identified here and here, we zoomed in, and then we had to go to 7 hundredths, which was the seventh indicator between 0.3 and 0.4. And then once we found that, right, here and here, we broke this little section up we zoomed in, broke that up into 10 pieces, and then we're going into the thousands. So we're going into the 2000s, just above that 0.37, okay? And yeah, so that was right there, 0.372. Right, so we have to be able to look at these visuals and have this really good understanding of where these decimals exist. So now I'm going to go down to that number line that you saw earlier, right here. And I want you to maybe sketch something like this on your own paper. And then I'm going to give you 3 different numbers that I want you to place on this number line as best you can, their approximate locations. So we're going to do 0.46, 1.75, and 2.271. So as best you can, sketch yourself a little number line that looks like what you see on my screen, and then see if you can indicate where those would be. Be as accurate as possible. So the first one, 0.476. If we look between 0 and 1, each of the segments between them are going to be our tenths. So this will be 0.1, 0.2, 0.3, and 0.4, and 0.5. 1/10, 2/10, 3/10, 4/10, 5/10. 0.46 is 4/10 plus 6/100. So we know it's going to be between 0.4 and 0.5, right? It's going to exist somewhere in there. Now, it's a little too small for us to actually make all those little indicator markings, but imagine making 10 segments here. 1, 2, 3, 4, 5, 6, 7, 8, 9, and 10 is on the 0.5. We want to go to the sixth one, right? Because each of these now represents 100th. So our 6 is going to be just about right there, right? Just about a little more than halfway. That's going to be our 4600th, or 0.46. 1.75, we'll do the same thing. Again, we know it's going to be bigger than 1. Here's our 1. Here's our 2. So it's going to be somewhere in this zone right there. Then we go to the next one, 7. This is 7/10. These are our 10th, 0.1, 0.2, 0.3, 0.4, 0.5, 0.6. Here's our 7/10. Here's our 8/10. So again, we're going to exist somewhere between those two. And then we have also 5/100ths. Again, imagine 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. This is going to be right in the middle, right there. 1.75. Now, this last one's a little bit harder, 2.271. We know it's bigger than 2. And then we go to the 2 here, which is 2/10. So where's 2/10? Right here, 0.2. This is 0.1, 0.2, 0.3. And then we have 7/100ths. So again, we're breaking up this segment between 0.2 and 0.3 into 10 pieces. 1, 2, 3, 4, 5, 6, 7. So it's going to be about right there. There's about our 2.27. And then we have to go, this is almost impossible, right? If we imagine this thing, right, widen that, right, 0.2, or I'm sorry, 0.7, 0.07, and 0.08, right? Because we're looking at the hundredths places there. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, right? Imagine that tiny little section there broken up into 10 pieces. The 0.71 is going to be that very first one. It's hard to indicate, again, that level of detail when we're this spread out, but it will exist right about there, right? 2.271. So the scale of the number line that you're working with will sort of dictate what level of accuracy that you're able to do. All right, so that's our modeling, right? We like the decimal squares, but we can also show on a number line, and it is important to be able to do both of those things. So a couple other foundational pieces with decimals. Some of these might sound familiar from when we were working with whole numbers or with fractions. We talked about opposites. We talked about opposites when we were dealing with integers, whole numbers, and their opposites. Do you remember that opposites really referred to the negative number? Decimals have opposites then as well. We also call these the inverse for addition, or the additive inverse. So just like we had with fractions and fractions and whole numbers, we have opposites with decimals. So 1.2 and negative 1.2 are opposites. They're reflected over the number 0 on that number line. And so again, when you add opposites, you get 0, right? Any two numbers that are opposites, if you add them, they're going to add to 0. So I just wanted to make sure that we address the fact that decimals also have opposites. Another really important concept with dealing with decimals is what we call the equality of decimals. This is familiar to us. We did a lot of work with fractions and finding common denominators, and we showed that two fractions can be equal even though they don't look the same. Decimals are the same way, and they're it's related to that same concept of fractions. And so here is a great example. And again, you have manipulatives that look like these as well. Just by looking at those three pictures, if we just examine the shaded areas, it's the same amount of shading in each one of those pictures. From here to here is the same as from here to here, and is the same from here to here. But notice the numbers themselves are written differently. This one is written as 0.4, which is 4/10. This one is 0.40, which is 40 hundredths. And this one is written as 0.400, which is 400 thousandths. As fractions, think about how those would look. 4/10, 40 hundredths, and 400. Remember, we always go by that last decimal place that is showing thousandths. And think about how this is connected with common denominators. If you multiply 4/10 by 10 and by 10 on top, you get 40 over 100. Same thing here. Multiply 40 over 100 times 10 and times 10, and you get 400 over 1,000. These are the visual representations of those. So it's okay, based on the situation that you're working with, to interchange these with each other, right? Whichever is the appropriate one for your scenario, that's what you are going to use. And just to test this a little bit, I'll give you a decimal, and then what I'll ask you to do is rewrite it to a different last place value. So if we write this, 0.35, and I say, I want you to now write that same equal decimal number, but to the thousandths place. Thousandths. How would you be able to rewrite that number to the thousandths place? Well, we could write it as 0.350. Those things are equal. 35 hundredths and 350 thousandths are the same thing. Similarly, if we put 0.670 and we rewrite that, but stating it with the last digit in the hundredths place, what would that look like? We have a trailing zero here, and we could write it as 0.67. We could drop that zero and state it as 67 hundredths. And again, that's going to be an equal decimal. Finally, we could put 0.600 and say, I want to write that, but only state it to the tenths place. Again, because it has these zeros at the end, 600 thousandths could also be written as 6/10. Again, they represent the same amount of stuff. So that was the equality of decimals. We also need to examine the inequality of decimals. Inequality of decimals. So when we refer to inequality, we're often referring to using these symbols: is less than, is greater than. So identifying which is more. This is something that students from elementary school all the way through college also often have difficulty with. And there are a number of sources of confusion for that. Let me give you an example. If I write 0.47 and 0.6, and often you hear me saying point, I do that intentionally because I want you to be the ones to think about the numbers using their correct language, and maybe for the sake of the problem that we're working on, not always maybe give away how you're going to be thinking about it. So how would we say this? 47 hundredths, this as 6/10. So which of these is greater? So what symbol would you put between these? Well, a lot of people new learners or people who maybe never got the full foundational concept of decimals might say this. Maybe you're one of them. You might be inclined to write that because you look at this as 47 and that is 6, and you're thinking 47 is bigger than 6. But that is not the case. That is not the case. This is the correct ordering of that. 47 hundredths is less than 6/10. We can illustrate that in a number of ways. Moments ago, we talked about the equality of decimals. 6/10 is the same as 60 hundredths. When we give the same number of decimal places, then it's often easier to see. It's kind of like getting common denominators in fractions. It's easier to compare them if they have the same denominators. With decimals, it's easier to compare them if they have the same number of decimal places. Another great way to illustrate the inequality of decimals is with our decimal squares. You can see it right here. 0.47, 47 hundredths. If we fill it in, looks like this. 6/10 looks like this. Notice they're divided up into different segments. And so we're doing a different amount of shading. So we can see that just by looking at the shading, the 6/10 is obviously much bigger, takes up much more of the square than 47 hundredths. We can also do something called the place value test. And the place value test for inequality of decimals says the greater of two positive decimals that are both less than 1 will be the decimal with the greater digit in the tenths place. If these digits are equal, the test is applied to the hundredth digit, etc. I love putting these definitions out there for you because often they're not written in the most user-friendly form. And I like you to be able to then try to process it and make sense of it. So if you haven't done it yet, pause this and see if you can make sense of what this is saying. So essentially, what we are doing here is we're going to take a couple numbers and compare them. I'm going to start with these 0.19 and 0.036. And we're going to determine which is bigger. Now, the definition says the greater of two positive decimals. Okay, so again, we're only focusing on decimals that are less than 1. So there's no leading whole number out front. So the greater one will be the greater digit in the tenths place. So if we just examine the tenths place here and here, that's all you need to do to compare these. 1 is bigger than 0. If you think about what the manipulatives would look like, the decimal squares, this one would have an entire first column filled in, an entire 10th column. If I scroll up and show it, it would have an entire one of these filled in, plus some more. This one would not. This would have nothing filled in. It would not have an entire column filled in. It would have other stuff filled in, 36 thousandths, but it would be less than a tenth. And so we can say just from comparing the tenths places that this is larger than this. So now what I want you to do is take that thinking, and I'm going to give you 4 numbers, and your job is to put them in order from, we're going to go from least to greatest. So I'm going to do 0.19, 0.036, 0.195, and 0.2. So take a moment and see if you can arrange those numbers in order from least to greatest. If we use the place value test, we see that comparing the tenths places, we have a 1, a 0, a 1, and a 2. So this one must be the smallest number, 0.036. Then we go, and so we're done with that one. I'm just going to cross it off. Because 0.19 and 0.195 have the same tenths places, we go to the hundredths places. Well, those are also the same, 0.19 and 0.19. So then what do? We go to the thousandths place. Well, this has a 5, and this doesn't have anything. So there is a 0 there, even though we don't see it. 0 is less than 5, so this would be our next biggest number, 0.19. We're done with that. Now we're comparing 0.195 to 0.2. We go back to the tenths comparison. This is next. So 0.195, and then 0.2 is our largest decimal. We can see that here with, if we look at this visualization, or at least those last 3, right? We can see that 0.2 has 2 full columns, right? Which is more than here, and it's more than here. If we look at 0.19 and 0.195, here's an entire first full column. Here's an entire first full column. And if we zoom in and you look at this stuff right here in those thousandths place, that's the same as these. That's worth 9/10. 1, 2, 3, 4, 5, 6, 7, 8, and 9. But then we've got these 5 extra little tiny sections, which are those 5 thousandths. So we can see that 0.195 is larger than 0.19, which is why it belongs next in that order.